And so let's get this started. This is the final session in the Careers in Tech Summer Series. I am working with a chapter up in New York, I believe, to do a hybrid session late September. So that meeting will be posted here in the next couple of days, probably. But in the meantime, I want to thank Jon for joining us tonight. He's one of the Computer Society's DBP speakers. And without further ado, I'll pass it along to our speaker for the night.
Okay. Are we live? Should I bring up my slides?
Yep, we are live. Let me go ahead and switch sharing over to you. Okay, so now you should I have stopped my sharing, so you should be able to share now.
Need a picture, do I? Okay. I'm looking for the share button. I know it's here somewhere.
Yeah, it should.
Start screen share. Okay, I got it. So yep. Just launch into it.
Yep, and it should show you up on top of the slides, or on the side. I forget exactly where, but once you start sharing, it should show your slides, which it's not showing them just yet.
All right, so I'm going to put my slides in presentation mode.
Yep.
All right, well, then I guess I'm just ready to go, huh?
Yep, you're ready to go.
Okay, well, hello, everybody. My name is Jon Peddle. I'm with Jon Peddle Research, and we're a research firm specializing in computer graphics. That is a very broad subject, believe it or not. Covers everything from GPUs to CAD software and image processing and everything in between. I've been involved in computer graphics probably longer than I should say, but since the early 70s. And I'm a member of SIGGRAPH, which just celebrated its 50th anniversary, as well as a member of IEEE. And I've built these things, and I've played with these things, and I've certainly recorded their behavior and their progress over time. So I'm going to take you for a little tour through the history of computer graphics. And it's a little difficult because it's not a straight line, and there are multiple disciplines involved. There's mathematics, there's photography, there's silicon or semiconductors, there are applications, just on and on it goes like that. And so to pick any one of those would be one way to tell the history. I've taken the adventurous route of trying to pick a couple of them and tie it into a continuous and hopefully understandable story. So this is an example of what happens. We create.
You can't see.
Yeah, we can't see the screen yet.
Oh, what should I do? Pause. Go back.
You'll want to pause.
I did pause.
Let's see. That's okay. Hang on 1 second.
Down at the bottom of your screen should be a. If you put the cursor there,
yeah.
Depending on your thing, you should see this thing that says share screen.
Yep, did that.
But you're not.
Then you need to select the application that you're sharing, which would be PowerPoint, and then you need to click share.
Yeah, the problem is I have a very elaborate multi-monitor system. There we go. Okay. There's that.
There we go.
Okay, so
There
now
we go. Yes.
Logistically, what should I do? Start at the top?
Yes.
Okay, it's not going to be as good as it was the first time.
It's all right.
And put your applications sharing in display mode.
Yeah, I'm going to do that now.
Okay.
Okay, I'm ready. I'm ready to rock and roll. If you guys can bear to listen to that. Again.
Yeah, but we're still seeing each individual one on the left.
Yeah, I'm going to click on it just a second.
Okay,
yeah.
Sorry.
Okay. No problem. There you go.
There we go. All right.
Okay, so hello there, and thank you for joining this session. My name is Jon Peddle, and I'm with Jon Peddle Research. We're a consulting and consulting firm in computer graphics. That includes everything from semiconductors to applications like CAD and 3D modeling. applications and all kinds of incredible technical things in between called APIs and drivers and other types of specialized software, including AI. I've been around in business since the early 70s. I'm a member of the IEEE, and I'm also a member of ACM, which includes SIGGRAPH. SIGGRAPH just celebrated their 50th anniversary, and I have some final words about that. So I'm going to try and tell you the story of computer graphics, and it's difficult to do because it's A, not linear, and B, it's not singular. There are several stories of computer graphics. There's a story of computer graphics applications. There's a story of computer graphics display devices, the story of computer graphics semiconductors, and on it goes like that. And I'm going to try and weave all that together into one story. So it may seem like it's jumping around a little bit. That's unavoidable. I apologize for it if it gets confusing. But I'm available through email if anybody has any follow-up questions or wants to find out what I said or what I meant or what I think about things. So here's examples of the kind of imagery and stuff that goes on in computer graphics today. But of course, it wasn't always like that. And this came about because of the Cold War, believe it or not. But the story actually starts way before there was a Cold War. It goes all the way back, excuse me, to 400 BC, and some of the very, very early mathematicians. As you can see from this chart, even this chart, which is designed to show linearity, jumps all over the place. Now, the chart kicks off in 1950s because that's when the hardware started to be able to actually do something with the math that already existed. And some of that math is called conics and Bezier curves, surface patches, nerves, things like that. And I'll touch on all those things. I'm not going to go into great detail on all those things other than just to make you aware that they do exist and that they have a part to play. I promise you there'll be no math involved and there'll be no Q&A afterwards for you. For me, there can be Q&A. 3D wireframes ran on mainframe computers originally, and just barely, I might add. Today, you can run them on your smartphone. Simulators are one of the early devices that were used to employ computer graphics. I think you probably know that 3D gets used in the movies, and it certainly gets used in games and things. It's used all over your smartphone. It's used on just about everything that you can think of today. So it's hard to escape it. And I don't know that we want to. So this block diagram represents the concept of computer graphics in a computer, or a 3D computer if you want. And I'll be referring to this as we go through this discussion, as each one of these boxes has a role to play. So 3D graphics has been realized through the pioneering discoveries of the Egyptians, and then the Renaissance artists and got it. Other geniuses in more modern times got it. But it all comes down to math. There's just no escaping that. Computer graphics is math. And if you're going to be a practitioner, now if you're just going to be a user, like maybe say an applications user or a CAD user or so forth, there's not so much math involved. But if you're going to build these systems or write the software, then there is math involved. So this guy is the guy who kind of kicked it all off. He started thinking about how geometry, well, he created the idea of geometry, but what is geometry? What's the relationship between squares and triangles and circles and even spheres? He thought about spheres, and he was a real pioneer. And he may not have been the only one, but he was a pioneer whose work was recorded. And that's a big thing when you're looking at ancient history like this, back to 500 BC. There are other people doing things, but they, for whatever reason, didn't record it. He influenced this guy, who I think everybody knows, Pythagoras. And Pythagoras worked out the math for the basic elements of a triangle. Pythagoras' theorem, I'm sure you all know that. The triangle is the smallest indivisible element we have in geometry. And it's the basis of all computer graphics. Every bit of computer graphics that you see, there's a triangle in there somewhere. So Thales introduced deductive reasoning. Thank you, Thales. Euclid took the ideas and teachings of Pythagoras and developed that into his own work called the Elements. And Euclid gets a lot of credit for his encompassing work that he did in mathematics. He kind of brought it all together, added a little bit more, of course, but he's the father that we kind of point at when we talk about geometry. But even as great as he was, something was missing, and that something would be a zero. And we probably take zero for granted in our lives, but it was a confounding and confusing thing for the people who were trying to deal with it. Now, zero can be used in two ways. It can either be used as a placeholder, 10, 100,000, et cetera, or it can be used as an actual number itself. Using it as an actual number was the thing that had confounded people. I once taught a class to a bunch of people, and in the class I had, it was in Texas, I was teaching the class, and in the class I had a good old Texas boy, and I had another guy who was an ex-Marine, and they absolutely struggled with the concept of zero being a number. They had in their mind that zero represented nothing, and it was almost impossible for me to pull them out of that thinking and make them understand that zero was the center point between real numbers and imaginary numbers or minus numbers. It was difficult. Well, if it was difficult for them, imagine how hard it was for people back in the Renaissance. The Babylonians actually invented it a long time ago. The Greeks banned it, as it says. The Hindus worshipped it. They thought it was a magical door to the universe and could understand it. And it scared the hell out of the Christian church. They used it to fend off heretics. Today, zero is at the heart of one of the biggest scientific controversies, and it's tied to one of the biggest discussions in both physics and astrophysics and quantum mechanics, where we're trying to define and pool all of the theories about the world into one theory. And the only way you can do that is if everybody agrees on what zero is, and in some cases where zero is. So it's believed that the first definitions of conic sections, and this is where we get into the extrapolation of geometry, goes all the way back to Meschinos. I can't pronounce his name properly. But you can see that if you take a conic cone, that's a round one, you can get all these other math functions. And these other math functions are essential to understanding, A, how things work and how the world is built, and also to creating computer graphics. All of these curves that you see, you can probably find on your car. The curves of your fenders and the curves of the hood and the trunk and so forth. There's not a flat surface or a corner on a car. The car represents the most elaborate display of differential curves that you're ever going to come across. Then there was Omar Khayyam, and he came up with an incredible geometric method for solving cubic equations. And that was basically intersect a parabola with a circle. Sounds trivial today because we studied this in high school, but for them, this was genuine rocket science back in those days. So we have the basic math. The next step is we have to convert that into algorithms. Algorithms are basic rules or steps or a recipe, but it basically tells a computer when to do what type of math and what to do with the answer. And so it sounds simple. It sounds, almost trivial, but it's very, very hard. And it's one of the biggest opportunities and one of the biggest problems that we have in computer graphics programming today. So that leads us into surfaces. But before we can get to surfaces, we have to understand just a little bit more about curves. And understanding curves and then applying them to a practical basis, such as my car example that I gave, has been difficult. It's been extremely difficult. And in the old days being, 30 years ago, maybe 40 at the most, it was done manually and it was done empirically. These little black things that you see in the picture are called ducks. And what their job is to hold a flexible piece of wood that you see there to create a curve. And the curved shape was depicted and selected by a designer without any math, but just on the basis of how he or she thought it should look. And what you see happening right here is they bent that piece of wood around and they're going to trace it. That's what that pencil's there for. They're going to trace that thing around, and that's going to become probably the hull of a boat. And that's how they did it. That's how they built boats. That's how they built cars. That's how they built airplanes. That's how they built anything that had a curve in it, until a guy by the name of, I'm going to have trouble with his name too, Schoenberg, developed a description of curves. And he introduced the idea that you could break a curve up into a whole bunch of tiny little pieces, which he called B-splines. That was then taken to aviation. And this iconic airplane, this P-51 airplane, Mustang, was the most popular airplane in World War II. This was the first airplane to be designed, all those curves, using math and not the ducks and the little flexible piece of wood and so forth. So we're making progress here. We're moving on. And you see where it says Loftsman, it's a North American loftsman, Ray Liming. Loftsmen were guys who did lofting. And what lofting was is you'd roll out this gigantic piece of paper that would be as big as the thing you're going to build, or at the very least, as big as major sections of it. I mean, they had huge tables that were 20 feet long and 10 feet wide, and they would put the paper on it, and the paper would become the template for the thing that we're going to build. That's how it was done in the old days. Well, we got past that, and we learned how to make curves. And not only did we learn how to make curves, we also learned how to generate them in a computer. And you have to remember, or maybe you don't have to remember because I haven't told you yet, but in the old days being the 50s and so forth, computers had very, very little memory, and it was very, very expensive, and it was also slow. And so to take a big equation, just even a simple differential equation, and put it into a computer was a major operation. And so we worked our way through that up until the time we got semiconductor memory, and I'll get into that a little bit later. But in the process of doing that, more math became available, and three-dimensional NURBS, which is what this picture represents, was another breakthrough. I happen to know, and he's a good friend of mine, actually, the guy who invented NURBS. One of the leading organizations that has pushed the development of these curves and things has been the automobile industry. And Henry Garreau is one of them. He did it, and he took facets, which is the picture on the left here, flat shaded things, and smoothed those together with math to make a nice smooth surface. The next step was do it three-dimensionally in a sphere. And Fong did that. And both of these guys were working for either directly or as consultants to the automotive industry. All of that led to what's known as the teapot. And the teapot was an experiment that was done in, I think now when it was done, probably the late 60s, early 70s in Utah. And the idea was to take some of these algorithms that had been developed by the previous authors I mentioned, and a few others, quite a few others, and do something with them, and at the university. This was done at Utah University. And so this teapot was rendered because, like an automobile, it has no flat surfaces, it has no right angles or anything. It's a curvy mess. But this has become an iconic symbol in computer graphics, the teapot. Everybody refers to the teapot. And it's used again and again and again in examples of something done in computer graphics. When some new, bright, young person creates a new algorithm or makes another older algorithm run faster, to illustrate that, they very often use this teapot. So if you're going to go into computer graphics, this teapot will be your friend. So that gets us into the applications of, we have algorithms, we have the math, now we're going to bolt it all together and turn it into an application. And you have some of these applications on your smartphones, and you certainly have them in your computer that do some of these things already. So where does 3D go? Well, it goes everywhere. And you remember my opening comments that it's difficult to have a story about computer graphics. If you look in the far right here of all the applications, you can see the reason for that, that each one of these applications, molecular modeling, aerospace, photorealism, vehicle training, so forth, they all have a story, and they all could tell a historical story about how computer graphics makes that particular application, the thing that they care about, come to life. And then one box over, you can see the major industries that are involved in this: the gaming industry, movies, simulation, biomedical, etc. That's why I say that computer graphics is just everywhere. It's almost everywhere that you can possibly imagine. So the first computer graphics applications were on big old mainframes. And I have a couple of pictures I'll show you in a little bit. And those big old mainframes started out working with relays. Relay was a nice off-on switch, and that's all any computer processor is an off-on switch. That graduated to vacuum tubes. Then we got the transistors. Transistors got smaller. We made them integrated circuits. That became microprocessors. And we went on and on to the point where we have mobile computers or smartphones at the bottom. And you see that took about 50 years or so to get from the relays to the handheld devices. So here's some of the stuff that goes into that. And drivers is a special software that communicates between an application and some hardware and the operating system. The controllers are the things that you and I perhaps touch, such as a mouse, a light pen, but they're also the processors inside the computer. And so we have this complicated soup, if you will, of all these different things, and they all have to work perfectly, and they all have to talk to each other, and they have to operate in synchronization. So it's not trivial to do all this. And yet, when you look at what's accomplished in the form factors that we have today, it's absolutely miraculous, I think. And that got us to CPUs and system memory. Now, these are old computers, really old computers. See that one there goes 82 BC? It's not fully understood what that thing did, but it's been cleaned up even more than this picture that you see here. It was found at the bottom of the ocean off of Greece, and it was thought to be a navigation aid that would keep track of the sun as well as the stars, and use that to translate into latitude and longitude for sailors and for people who are taking material and stuff from one country to another country via the ocean. Well, the ocean doesn't have any signs, so you need other ways of finding your way. The next step was a computer, which was called the Jacob Land, and you see that those things that have little holes in them, those were actually programming. And the concept of using those programming designs led itself later into a thing called punch cards in digital computers. So all those holes that you see is actually binary, and it represents ones and zeros, but it represents ones and zeros for thread. So that would turn on a loom and have a thread woven in, and if the next step didn't have it, the thread would be pulled back and it wouldn't be woven in. And if you look real closely to the left of that thing, you can see there's a pattern of tapestry or something there. That was made using those type of things. That loom, by the way, still exists. It's actually functional, believe it or not, at the Manchester Museum, Manchester, England. You can go and make cloth if you have enough time to stand there and push the levers and so forth and make it all work. But they do that at the museum every day. The next machine is called the difference machine. This was done by Babbage, Charles Babbage. And this particular machine is in the Science and Technology Museum in West London. That's my personal photograph of it. So is the other one, by the way. Anyway, this device sought to solve the problem of mathematics using analog rather than digital. And the analog in this case was levers and wheels. And you put in the program on a piece of paper, and dials would turn, and one dial would turn another, which would turn another, almost like an automobile transmission. And an answer would come out sometime later. There'd be a guy, you can see it just barely on the left, those two big gears. There'd be a guy there cranking it, right? And he would crank it until the answer that he was looking for came out. The machine was actually never really finished. Babbage ran out of money. His sponsors gave up on him. Other countries like France and Germany tried to copy it, and eventually it just faded away. It was just too complicated. The biggest problem they had was they didn't have the machining skills in those days to build the precision for the cogs and the wheels necessary to make it work. Much later, a wealthy Silicon Valley billionaire had one of these built from the original plans, and he has given it to the Computer History Museum, which is in Mountain View, California. So if you're ever out that way, go to that museum. You can see what this machine does. His works, because he was able to build it with modern precision machinery. The next one is the Zeus Z1. This was the first functional digital computer. It used relays, electromechanical relays. And the guy who built this, Mr. Zeus, he built it in his parents' basement. That was his laboratory. He built it as a home project, as a hobby. He just wanted to see if he could get it to work, and he did, in fact. His work was interrupted because of World War II, and he left, did his duty, came back, finished it. And these things actually went into production. And Siemens, for example, had one of these running up until as late as 1990, believe it or not. It did a certain thing that they wanted done, and it was easier to keep that thing running than reprogram a whole new computer. The first vacuum tube-based digital computer is by the Anislav Berry. Anislav was a professor at the University of Iowa, and he built this machine. Well, actually, he didn't build this one. This is a replica of it. But he and his grad student, Berry, built this in 1944, just as the World War II was winding down, kind of. Two guys from Philadelphia went to visit him, and unfortunately, I've forgotten their names. But anyway, they saw what he did. They came back. They made a proposal to the U.S. Army and the U.S. Navy that they could do it also, and they built the ENIAC, which almost everybody has heard of. And these guys took credit originally for inventing the digital vacuum tube computer. They didn't. They copied it from Anislav. Finally, in a suit sometime in the like 1970s, I think it was, the truth came out, and these guys said, yeah, okay, we did go to Iowa, we did take pictures, we did make notes, and yeah, we did get our ideas from there. But in the meantime, the folklore of the first computer being ENIAC. ENIAC was used by then MIT and what's now Bolt, Bangerack, and Newman to build the Whirlwind computer. And here's where we go. This is the kickoff of computer graphics computers, this Whirlwind computer. And we'll have a lot to say about that. But remember Whirlwind, because it plays a role in this whole story. So there's another picture of the Whirlwind, and in the late 50s and early 60s, if you had a graphics computer, that means you had all of the stuff you see here. All of that was necessary to make a graphics computer. Now, get perspective here. All of that to make graphics computer, and now in your pocket is a graphics computer, and it's far more powerful, and it has much higher resolution, and it's much faster, and it's also a hell of a lot cheaper. So that's the kind of progress that we've made. But just look at what we used to do, and these machines were programmed with wires, and you change those wires for every little program that you want to do, because they didn't have memory. So the wire plugging was actually the memory. We evolved to the point where we had standalone displays, and you can see the size of that. That tube, by the way, is an outgrowth of an old radar tube. And the typewriter that you see there is the input device. So she's holding what's called a light pen. And what a light pen does is it actually sees the light coming out of the CRT there, and it knows where the light on the CRT is. So that's its XY coordinates. And so she can annotate that. She can say, move this curve over, or maybe she can say, add this particular annotation that's a number or a letter or something like that. And that's how people dealt with computer graphics in the late 50s, early 60s. Well, computers shrank, and we got things called mini computers. And there's, very famous PDP mini computer, PP11. And that box that you're looking at there is probably, maybe 18 to 24 inches tall and about the same width, maybe. So it was, it wasn't tiny, but it was a hell of a lot smaller than that big room of stuff you saw in the previous thing. Then we put computer graphics into standalone displays. Here he is with LightPen again, and his printer. And that became workstations because they had high performance and it had high resolution. And that were the two requirements for a workstation, something you could do serious graphics work on. It evolved and evolved, and we got microcomputers. This was the precursor to the PC. And microcomputers did an enormous amount of work. I wrote my PhD on a microcomputer. My biggest problem was keeping the paper straight. And so then this evolved further, and now our computer has become the display, and we call it a tablet. So it went on like that, and it'll continue to go on like that. It was confusing, it was messy, it was really exciting. You never knew exactly what was going to come out of your experiments. Sometimes there was serendipity, sometimes there was tears, but things kept moving, and more people joined the industry, I don't know how to describe the community. That's it. They joined the community. So we had universities working on it. We had big companies trying to solve problems, building airplanes and cars. We had experimenters working on it, like the guy in Germany in his basement. And it was just, it was everywhere, and it was nobody in charge. So here's Mr. Berkeley, of the famous Berkeley, showing his Relay personal computer back in the 50s. He was kind of behind Mr. Zeus, but nonetheless, he had the same idea, and it was independent. He didn't know of the German guy or vice versa. They were on the same track, doing the same thing, and this guy just was a little bit slower in his response. Then in the early 70s, a company in Texas called DataPoint, used to be a competitor of mine, came up with the idea that they would build what's called a glass teletype, because a teletype machine, which was basically like a big typewriter that you would type on mechanically, it would print bang, bang, bang as you type, but at the same time, it would punch holes in a strip of paper that was about 1 inch wide, and those holes would become a program. And it was the input and sometimes output terminal for mini computers and other computers for a very long time. And so these guys at DataPoint said, well, why can't we do that all with semiconductors? And instead of having paper being printed on, why can't we show what's being printed on a CRT display? And the answer was, you can, and they did. And so you could argue that was the first PC. The counterance to that argument would be that it really wasn't, because it wasn't for consumers. This was meant to be an office product operated by people who knew something about computers. But just a few years later, we had a microcomputer like the Commodore PET. There was another one by Radio Shack, and they really empowered the hobbyists. That PET, by the way, that's the machine I typed in all of my words of my thesis. Machine just like that. I built a separate memory buffer in the back of it to expand its memory for the display, but that was the device. Later, we kept moving along, kept the same concepts going, and we developed the first workstation down there in the lower corner. And that really doesn't reveal all the stuff. There's another box that's missing from that picture to make a workstation work in those days. But now we were replacing the light pen, where people were tapping on the screen to find out where the cursor was. Now we were replacing it with a digitizer tablet. That's the thing to the right there. And so then what we could do is we could draw on that, and it would convert our drawing into bits that would then go into memory, and it would be a record of what it was we drew. Then we display it. We'd find the errors in the digitizer, try and smooth that out, maybe annotate it, add some more stuff and so forth. And that looping process was the way engineering drawings got made in the 60s, moving into the 70s. Moore's Law, which I'm sure you've heard of, changed everything because Moore's Law does work. And by the way, it is still working. Don't believe what you may hear. And the idea of Moore's Law was that we would increase the density of semiconductors every 2 years or so. And by doing that, we would either decrease the price of whatever we had built. Let's say we were building a 16K bit memory device, and it cost $100. Well, 2 years later, that same amount of memory, 16K bits, would be $50. Or we'd have 32 bits of memory for $100. So the idea was you could either drop the price, keep it in the same size of what you had, or increase the capacity, but keep the same price. And that's been the magic of Moore's Law, and that's what has empowered so much development in computers and in computer graphics. The following chart, the next chart, shows the evolution of displays and how we have gone from raster terminals to vector terminals. Those big displays that I showed you earlier that had the guy with the little light pen on it, tracking it, those are vector displays. And they would draw a line on the screen from point A, point B. It would be a perfectly straight line. People actually used to use a ruler and measure those lines on screens to make engineering drawings. They'd measure the screen, they'd write it down, then they'd make a drawing. That was because we just didn't have the memory to do it. So vector terminals gave way to raster terminals, and raster terminals use a scanning process, which is how your TV works. And the TVs were being produced using raster, and so their tubes, their displays were less expensive than these big old former radar tubes that were being used as vector terminals. And so we took a quantum jump in cost, but at the expense of resolution. So the big old radar tubes had fantastic resolution, equivalent to 2000 by 2000 pixels. The new raster ones, seldom got above 480 by 240. Just barely a little bit better than what TV was at the time. But those things all yielded to Moore's Law. So that got us to the graphics processor and the frame buffer. Frame buffer is where the image is stored in the PC or the computer or what have you. And then we go into controllers. Now, this is going to be a tough chart. I'm not going to spend a lot of time on this because I could spend all day on this. But what I want you to get a sense of here is that the hardware versus the market and the software is that the software moved very slowly, I'm afraid to say. It didn't move as fast as the hardware, and it still isn't. The software is always a little bit behind the hardware. But the hardware was moving. We had controllers, we had discrete logic chips, then we got VLSI, it stands for very large integrated circuits. We got high-speed memory. We struggled through communicating between these processors. So to communicate from a CPU to a graphics processor, we had to go through a bus. Buses became hard to manage. They used a lot of power. So then we evolved to what's called PCI, which is serial transmission. And that's much, much more efficient. That's what we're still using today is PCI. And we started to fill out the PC. So the first bit-mapped AB add-in board is what AIB stands for. And maybe I just ought to poise for a moment and explain bitmapped because I just say it and expect everybody to know what it means. If you're looking at this screen, you're looking at a bitmapped image. And what that means is that each little pixel on here, on this screen, on your screen, little dot, you can't see it unless you get your eyeball right on the screen, you have good eyes, but that is a bit. It happens to be a display bit. And up until the PC was invented and it became available as a consumer device as well, they had really lousy graphics. And this company, Hercules, and started in Berkeley, California. You see that card there, that's all memory. And that's the memory, that's the frame buffer to store a bit-mapped screen that was of the gigantic proportions of 700 by 300. right? You can do the math on that, right? That's 21,000, and that was a big deal, and that board revolutionized consumer electronics and computer graphics kind of in general. The next step was Matrox. That's a Canadian company still in business, and they were one of the first ones to build a 3D graphics board. And if you look closely, you can see there's actually two boards there. They're sandwiched. The second board is all memory, and most of this first board is memory as well. And it doesn't take much imagination to realize that if you have a 2D picture and you convert it into 3D, you've just quadrupled all of the information that you had. And that just takes a lot of memory. That board, that 3D board, wasn't terribly successful because the market wasn't quite ready for 3D and PC yet. That takes us down, leaping by a couple of decades now, to a modern day board. And this modern day board, this particular one here, for example, that could have as much as 16 gigabytes, bytes, not bits, 16 gigabytes of memory. And we just kind of take that for granted. We talk about 8 gigabytes, 24 gigabytes, and so forth, just like that. It was a miracle in those earlier days to think about such things. The market for these devices, these 3D graphics controllers, like those boards that you saw, actually the chips on the boards, took off. When we started to realize that we could actually build these things, lots of companies entered the market because they saw the opportunity, they knew the demand was there, and they soared up. And then we had a recession, and the market started to fall because these companies that were all startups couldn't get any new funding from the venture capitalists. And then just to make things even worse, we had the internet bubble pop. That's a different long story, but it was devastating to the stock market and consequently devastating to the investor community. So investor money just disappeared. But a few companies survived who were already established. They were doing fairly well. One you might recognize is NVIDIA. And NVIDIA in 2000 introduced a chip that was a fully integrated graphics pipeline. And what that meant is it could do transformations and it could do rendering. And NVIDIA dubbed that the GPU. Now, I've written 3 books, big, thick books about the history of the GPU. So I'm not going to try and summarize that for you now, just to say that NVIDIA didn't invent the GPU, but they were the first one to commercialize it and to make a consumer-based product out of it. And so they've taken credit for it and everybody gives it to them. And who cares about, a few historical details? But that's how the market went, and it came down. Now, this chart ends at 2016. Since 2016, some new companies have entered the field. So it goes back up. And we now have probably 10 companies making GPU semiconductors, and 2 or 3 more in the works of doing it. If they can get some more funding, they will do it. Which took us to the display. So we built the chips, we got the memory, the algorithms are running, applications are there. Now we got to show it on something. And displays evolved too, as you can imagine. And so the early dot positioning ones, the vector draw, I mentioned to you about how that works from point A to point B and so forth. That gave way to raster scanning. They were all monochromatic up until the 1980s, even past. And then we introduced color. I can remember being in a discussion with a company, it was a client at the time, and I was trying to convince them that they had to build, they were in the monitor business, and I was trying to convince them they had to build a color monitor. And they said, well, why do we need color? I'll never forget it. Why do we need color? I don't know. What a crazy idea. Anyway, so we got color. We also got new ways of building displays. And one that you're probably most familiar with is the LCD. We started out with CRTs, those big glass things that shot electrons at the phosphor screen. Then we evolved to LCDs, which are little switches in a crystal that you could turn the crystal opaque or you could turn it open. And when it was open, light shined through, and that's how an LCD works. That evolved to OLEDs. The O stands for organic. LED is light emitting diode. And that's very, very popular in smartphones. Almost all the new smartphones screens are OLEDs. And it's in larger, some TVs now also. It's a more difficult process to make, but it's early days still. And OLEDs will be the ultimate display of choice. So now we're going to jump all the way back But I told you I can't do this in a straight line, and try and tell the story of computer graphics a little bit differently. Back to that whirlwind computer, remember him? And what you see is a guy sitting there looking at a thing that's called an oscilloscope. And an oscilloscope is a CRT tube that can draw anywhere on the tube, pretty high speed, much faster than we can see it. So it's faster than our perception, our perseverance. And they're looking at imagery to design something or test something. And that was how we did computer graphics in those days. I shouldn't say we, because I wasn't doing it then, but that's how they did it in those days. But this is what made it happen. And maybe some of you have seen the movie Oppenheimer. Well, Oppenheimer inadvertently created the computer graphics industry, because when the United States exploded the atomic bomb, the people who were building it out in Los Alamos under Oppenheimer's direction had within their ranks people who were afraid of one country owning such a devastating weapon. And you can argue the politics and philosophy of that all you want, and it continues to be argued, but nonetheless, they were motivated to share the secrets with the Russians. And not too much later, the Russians were able to build their own atomic bomb, and did so in 1950. And when they did, it scared the pants off of everybody in the United States, because the fear was that Russia, which had now become the enemy of the United States for a variety of reasons, and we had entered into the Cold War. Nobody was shooting anybody yet, but they were threatening to do that. And the United States feared, and so did North America, Canada as well, that the Russians would fly from their bases in Russia straight north, over the North Pole, straight down into the US, and drop atomic bombs. And the Russians built an airplane, which looks very, very similar to a B-50 that was used for US bombers. In any case, they built it, and this lumbering giant had enough fuel and had enough lifting power that it could lift its bomb load, and it could actually make the trip. It was a genuine threat. The United States did two things. They built what's called the DEW line, which early warning is what that stands for. And the DEW line was to warn us that these planes were coming, because the DEW line consisted of a whole bunch of radar stations up near the Arctic Circle in Canada and so forth. And so if you try and, here's, we're back to geometry, visualize a sphere and an airplane is coming up. Well, if you're at the right point, you can actually see down into where that airplane's coming from. So this radar system that was built could actually see into Russia. And if these planes were coming in mass, and they were going to be in mass, then we'd get an early warning. And that would give us time to launch fighter jets to try and shoot them down. We had some primitive rockets that were called Nike rockets. And at the same time, launch our bombers to counterattack after the Russian bombers had come through and destroyed whatever it was the US. Anyway, that was the rationale, and lots of books have been written about this, lots of movies have been made about this. It was a scary, scary time. And it established budgets. That was the best part. And now we had to have a means of putting the radar stations there, getting the data back, putting the data in some presentable form. Oh, by the way, the communications from the radar stations to these central stations like this was done on existing telephone lines. So they were putting in new telephone lines at the same time they were building all this stuff, but it was telephone technology, very, very slow, that would do it. And so you can see there's two displays there, and the whirlwind computer, famous whirlwind computer. And those displays are basically old radar scopes, you know, from monitoring airplanes. And that's where guys sat and watched for any unexpected and unauthorized aircraft. And so here's an example. And you can see these guys, a little light pen there, and he's looking at radar. the displays improved. They got flat instead of being curvy. They got square, which I don't know why that's important, but it was. But light pen still, and you see he's looking at the East Coast there, identifying airplanes, friend or foe is what it's called. And this was the technology that fueled the computer graphics revolution that was about to start. So it didn't take long for this to get commercialized. And this is a PDP-1. This is one of the first, it's called a mini computer, but it really wasn't. But in any case, it has, and you see the big 30-inch display there. Again, it's a descendant of the radar scopes, but that was how we did computer graphics in those days. The round little wheels that you see sitting on the box to the right, that held this punch tape I was telling you about. And there's your keyboard, and that typewriter there. The reason it's so big and bulky, typewriter actually transmits keystrokes into a computer to create programming instructions. I have some personal history on interfaces with that. So we evolved, and as we evolved, we took on bigger and bigger problems. And one of the first problems that computer graphics was given to solve was molecular modeling, 3D computer graphics. And it's amazing because you'd think it could be almost anything else. I mean, the military was interested, were other people interested, but molecular modeling really caught on because it just was so easy to visualize chemistry with a reasonably performing computer graphics device. But simultaneous to that, we also developed what's called computer-aided design, CAD. And one of the first companies to do that was General Motors. This is a General Motors CAD system. Now, the problem here is we had a dichotomy of objectives and purposes in that the people who were doing molecular modeling were usually in universities, and they were wide open about what they were doing. The people who were working on cars were incredibly secretive and competitive with other companies. They didn't want anybody to know what they were doing. So it wasn't for maybe 4 or 5 years, possibly even longer than that now I think about it, 4 or 5 years that we actually found out, we as a general public found out what General Motors was doing. They were doing incredibly advanced computer graphics work secretly in their labs. Well, then it got to the movies, and the movies have never been the same since. And some of the first movies, Tron, maybe you've seen it. If you haven't, go see it because it's fun. It's a fun movie. The story's not real great, but it's fun to look at the graphics. One of the big things that was done was this Genesis sequence in Star Wars. And this is where they terraform this planet to bring it back to life. And the computer graphics of the terraforming as the foliage and everything is working its way over was an enormous computer processing experiment. And it took a lot of time. Nobody knew if it was going to work or not, and more importantly, would it work in time, but it did. Jump ahead 20 years, and it did take 20 years, and we were able to create imagery that looked like this Aki in Final Fantasy. That was the most profound movie. It was a full CG movie at the turn of the century, and the screens in here and everything don't do it justice. If you can find that somewhere, Final Fantasy, go watch it. It's a crappy story. I can't recommend the story, but the computer graphics, you just turn the sound off and just look at the computer graphics. It's really incredible. Now it's all over the place. You can't escape it. And not only can you not escape it, you can't detect it. And that's the best part. That's called suspension of disbelief. When you are watching a movie and you get immersed in it and it's just, to you, believable, then the computer graphics artists have succeeded. They've done their job. And when I tell people that Sandra Bullock in Gravity, most of the scenes are computer generated, that it's really not her, they think I'm making it up. They say, no, come on, I know Sandra Bullock when I see her. Well, yeah. Well, who do you think that is right there? That ain't Sandra Bullock. That's an animation. And you see the blue guy on top of the green dragon? That's not a real person either. That's all computer graphics. And of course, it evolved to games. Well, first thing we had to do in games was we had to get 3D working, and we had to get it working in a PC. Sorry, that went by too fast. I should have timed it out better. But when you play a game, look at all the stuff that's going on in your PC simultaneously to create the imagery that you see. And here again, it's suspension of disbelief and immersion. If you play a first-person shooter and you get really involved with it, I play first-person shooters and I get really involved with it, even though I know exactly how it's built, but you get so involved with it that you're in it. You're actually in the movie, right? Then the computer graphics is working. And look at all the stuff you have to do to make that happen, and even more. Now, the monitors didn't keep up with all of the graphics and the math and all the other developments and the memory and so forth, in that they didn't display enough colors. So your average monitor will display 8 bits primary. Primary is RBG, red, blue, green. That gets you out to 16 million colors. Sounds like a lot, but it's nowhere near enough. Our eyes see tens of billions of shades. I know that sounds extraordinary, but it's true. In this picture, if we were in this actual room, standing where the guy with the gun is, we would see, look at the far left column, we would see stuff behind that far left column. It's there. There's stuff there. There's stuff on the wall and so forth there, but we can't see it because the display can't bring it out. And to bring it out, we have to use what's called HDR, high dynamic range. I think I'm getting ahead of myself here in the slides. I didn't. Anyway, and so high dynamic range takes us from 8 bits per primary to 10 or 12. New monitors and new TVs have HDR, and you can see a whole lot more stuff. Problem now is the source of your stuff. So if you get a new TV that's HDR capable, and you're watching things on it, you can say, well, that doesn't look so great. What's so terrific about this? The problem you have there is the content. Content didn't render it, or content provider, Netflix, Prime, and so forth, aren't shipping you 10 bits of data because it's a lot of bandwidth. They just can't afford to do it. So you get tripped. But if you buy a DVD, you can get it. Well, now we've got computer graphics really working for us. We know how to make beautiful pictures. We've got displays that can display it. What do we do with it? Well, what we do with it now is we build things, but we build them in computers. So we don't go out and build a skyscraper and hope we got it right. We design it first, we ray trace it, and then we show it to the people who are going to pay for that building and say, what do you think? You like this one? And they say, no, we'd like it to be a little bit taller. We'd like it to be a little bit greener. And you go back to the computer and you change that. Same thing with a car. If you've seen any automobile advertisements, including videos, in the last 2 or 3 years, you've seen computer graphics. Because what you're seeing is in the computer, it doesn't exist yet. Because it's easier to fix things and sell things from a computer model than it is to build it and try it. So let's look at this car, for example. Suppose they built that, then took a picture of it, then went out to people and said, hey, would you like to buy a car? And you go, oh, I hate that car. That's terrible looking. You know, oops, what do I do now? I got these cars. So if you can do it with a computer ahead of time, pre-sell it, so to speak, and or fix it if people don't like something about it, that saves so much money. It's incredible. And you get a better product. So stuff kept coming together. Stereo vision. Remember stereo vision is 3D? Maybe you don't. That's when you have put on a pair of glasses and see depth. Tried it with TV. Didn't work. People didn't like putting on glasses and they lose them. Holography, we're still talking about that. It can be done, but it's just impractical from a physical point of view. Virtual reality, I'm sure you've all heard about virtual reality. It's still kind of a novelty. There's no real good application for it, and people get tired of wearing a headset. People get sometimes ill from it, get upset stomachs. Augmented reality, I'm totally stoked about augmented reality, written a couple books about it. That's, I think, going to be the big takeoff. You can do augmented reality on your smartphone, and you don't have to wear special glasses. But one day, we will wear special glasses that'll be no different than wearing sunglasses are today or prescription glasses. That means that they won't call attention to themselves. They won't embarrass you to wear them out in public because they'll look just totally natural, except that you'll be able to see stuff on the glasses that's not there. The next development was, in terms of trying to get reality and understand how things work and design stuff, was called a cave. And this was done at the University of Chicago Electronic Visual Laboratory. And what you see here is rear projectors. There's the projectors behind these screens projecting onto them and creating a 3D model. And if you look at those triangles or pyramids, whatever they are out there, you notice that they kind of look blurry, they're doubled up. That's because the guy, has a wire coming out of his head, that wire is to drive a pair of stereo glasses. So he's getting a 3D image inside of a 3D volume. And that was a major, major breakthrough. It also was very expensive at the time, 1991. Here's an example of how it gets used. These guys are walking inside a car and saying, this guy's saying, well, you know, that air vent should be moved over to the left a little bit. Back to the earlier point I made, while it's in the computer, you can move that air vent anywhere you want, right? You don't have to build that thing and then say, oh, Christ, we should have moved it. Now you just do it. They're wearing stereo glasses as well and examining a model. So again, they're looking at 3D inside a 3D volume. Well, caves are popular, but they're expensive. This one is amazing to walk into. You see this, boy, you instantly get immersed. It just, because everything in your brain is suddenly filled with information. It's inescapable. In fact, in many of these rooms, they have railings to hold on to because people get so disoriented from the thing they're looking at, they just tumble over. This is the biggest one that was ever built, the reality deck. It's got hundreds of displays to make it. And again, it's totally immersive. It's just unbelievable to walk into it. So this is the wrap. I mentioned to you about SIGGRAPH having its 50th anniversary, which it did this year, celebrated in Los Angeles. And I've been deeply involved with SIGGRAPH for several decades. And so they asked me to do this. I made this poster depicting the 50-year history of SIGGRAPH. You can see a lot of things on here that we've already looked at that were in the presentation. I have 10 of these left. And so it's a first come, first serve. Contact your sponsors and ask them if you want one. And like I say, whoever gets to me first, I'll be happy to send them to you. It's a fairly large poster. It's kind of fun to look at. It goes from 72 out to 2003. And so that's it for me. I hope some of this was interesting. And I hope I didn't talk too fast to make it, oh, goodbye. Hope I didn't talk too fast to make it unintelligible. So I'm going to stop sharing. And I don't know if we do Q&A now or what.
Yeah. So just as a quick bit of housekeeping, if you are an IEEE member and you have attended this session, please type in IEEE in the chat.
There's the chat.
Should be at the bottom of the screen next to share screen.
Oh.
Yeah, you'll see a whole slew of people typing in IEEE.
Yeah. Can I put the last slide up? Yes, I can. He said with too much confidence. All right, let's see if I can do it. And the last slide. Oh, the last slide would be that poster, I guess, huh?
Yeah.
Okay. And then this guy. Maybe not.
Oh.
No. It's struggling.
Yeah, it's because of the timing, I bet.
Yeah, I guess if we had enough time, we could wait for it. So the answer to your question is no, I can't. But let me try just one more time. Okay, so we can do it there. I can get it that far.
Yeah.
At the very least, I could full screen this so it looks like it's. See how this works there. That's a little bit better. And then where's my chat window? I've lost it. Well, I guess I can do one thing or the other. So yep. This is a simplex machine.
Well, let's see if there's any more questions here. Oh, it looks like you have a question where someone is asking you to explain the difference between a B-spline and a Bezier curve.
Ah, okay. That's a great question too. It's not going to be easy to answer. Bevier uses a more complex mathematical solution. B-spline you can think of as being a segmented curve, where it's a piecemeal operation, whereas Bezier is more of an integrated integrated calculus. It's more of an integrated connection in that it takes into consideration elements along the curve all the way to the end to arrive at the smoothness of the curve. Whereas a B-spline, you're just kind of slicing up. It's almost like faceting what a B-spline is.
They're actually wanting the actual very last slide, the one with your book and contact.
Oh, well, boy, I'm happy to show that one. Rush out to Amazon and get your very own.
It looks like Randy has a question. Go ahead, Randy. If you're talking, Randy, we can't hear you.
Yeah. Well, type it in, Randy.
Yep. Oh. Yep. Go ahead and type in the question. We'll handle it that way.
Well, while Randy's doing that, whoever's left on here looking at this, I want to thank you for looking at it. I don't know what time zone you're in. I'm in the last time zone, so for me it's still early evening, but for some of you folks it's got to be late evening, and I do appreciate you making that kind of investment.
It looks like let's see. It looks like so Randy says perhaps explaining graphics should include the rendering equation.
Oh, I said there'd be no math. That was rule number one. But the rendering equation is a good one, and I would encourage anybody who's interested in computer graphics, even if you don't consider yourself a math whiz, just to take a look at that rendering equation and understand the variables that go into it, because the rendering equation satisfies my lecture number 107 that I give people, that if you can understand a system, then you can pretty much understand anything. And the rendering equation does that. It consolidates all the things that we have to take in consideration to do rendering. It does it very eloquently. So that suggestion is really good.
And for John, he's saying, I'm interested in going back to school for computer graphics, but the math portion intimidates me.
Mm-hmm.
Isn't my best subject in school. Is there an intro program you could recommend?
No, I can't, is a short answer, but let me just fumble around a little bit. There are books, and if I can get a little bit of free time, I'll make a syllabus and send it to our organizer. But there are some books that are relatively easy to read. They do have math in them. You have to cope with a little bit of math. The basic math in computer graphics is transformations. So if you have some familiarity with matrix math, and it sounds intimidating just to even say that, it turns out it's duck soup simple to work. You shift things around and you get an answer. But that's what you have to do in computer graphics. Here's the model. Think about it like this: is you create the image, and when you create it, you're in some abstract space, some coordinate system that really doesn't exist. But then you've got to translate that into space, a coordinate space that is in the computer, in the graphics processor. And then you have to transform it one more time into the space of the display. And so you keep making these transformations. And that's the heavy lifting, if you will, of computer graphics. The other things that are math related, you probably don't have to worry about in terms of being able to create it. You have to be aware that they exist. Shading algorithms and things like that, they just happen now. You don't have to do it. You don't have to reinvent that wheel. You just call them. It comes from a library. So you do have to know programming, and there's 5 or 6 different languages now they're being used for programming, Python being one of the most popular currently. But through programming, you can say, draw a circle, shade it, highlight it, put some shadows around it in language just like that. You can almost speak literal English to it to get a picture drawn.
Yeah, it looks like the next question we have is from David. He's asking what your perspective is on projection displays and their role.
Well, they have a great role. You you wouldn't be able to go to the movies if we didn't have projection devices. Many of the special events that you see at places where buildings light up and all kinds of crazy things are going on in outdoor venues, that's all projection. Places to see the stars, what's it called? I lost the word. Planetariums. Planetariums are all projecting. And boy, planetariums are complex projection devices, because think about that. You're inside of a sphere, right? No flat surfaces. The coordinate system is crazy. And you've got to pinpoint and accurately where each star is and then move it, right? And it's going to move at a different rate and so forth than the other stars are. Very, very complicated computer graphics.
I think we've got time for one more question. If anyone has one more question here. Otherwise, I think we're going to be calling it a night, because it's, at least for me, it's nearing.
It's nighttime.
It's nearing about 8. It's almost 8 my time, and I know those that are joining us from Eastern time, it's even later than that. So just one more question, if anyone has it. Oh, so Neil has the last question here, and he's asking, any thoughts on the respective contributions of Ivan Sutherland and Jim Blind?
Jim Blinn?
Blinn, yes.
Yeah. Jim Blinn's a good friend of mine. Ivan Sutherland, I've met a few times. They are literally giants. I mean, they have made such enormous contributions to computer graphics. It's a long list. And Jim Blinn is the sweetest, most humblest guy you could ever met. He won a MacArthur Prize, by the way. He accepted the prize at SIGGRAPH. He stood up on the stage. He said, "Hey, I just got a lot of money. I'm going to build a place in Hawaii. Y'all come and see me." And Ivan Sutherland is just as modest. He doesn't brag about anything. His contributions are just endless. They're just extraordinary people. If you can find a book about either one of them, go read it. Their contribution. Blinn did a TV series for I think it was for NASA, called The Mechanical Universe. In fact, the person that asked the question about computer graphics, find Blinn's Mechanical Universe videos. They're probably on YouTube somewhere, and just invest the time to work your way through that, because Blinn, who is a mathematician, leads you through the math of computer graphics in such a delightful way. He's got beautiful pictures that illustrate what the math function means, and he doesn't beat you over the head with the equation, but rather he shows you this is what that equation will do for you. So that would be the answer to the person that asked about elemental computer graphics tutorial.
And it looks like John is asking whether you have met Steve Williams or Mark Dipp, D-I-P-P.
No, I don't know those names.
Okay.
Should I meet them? Send me their email. I'll contact them.
All right. I know there's been some questions about the recording. The recording will be going to Animators for Jurassic Park.
Well, you guys can see my email address, and I try to answer all emails within 24 hours. So if you send me an email, you'll get an answer.
Yep. And so for those of you that are still here, this session was recorded. It will be posted probably by Tuesday, hope maybe a bit earlier, just depending on how long it takes for it to process and get up to the YouTube channel. But it will definitely be posted, and I'll be sending out an email to whoever registered with the link on that.
Will it be open to the public or just people who signed up?
It'll be open to the public unless you want it to be unlisted.
No, I say do that because we'll advertise it on our webpage also.
All right. So I think that's everything for tonight. Thank you everyone for participating in the Careers in Tech Summer Series. It'll be on so the question is, where will the video be posted? It will be posted on the it'll be posted on the YouTube channel for Northwest Florida IEEE. So it'll be at NWF IEEE on YouTube. And I think, and I'll go ahead and type that into the chat for those of you that want it. But there'll be an email that'll be sent out to whoever registered for this talk as well. Thank you to everyone for participating in the Careers in Tech Summer Series. We had over 800 total registrations across the 10 events that we had. 436 participants, including 56 tonight. And it looks like we hit a participation percentage of around 53%.
That's pretty good, especially given the time of night.
Yeah. So again, thank you everyone for joining us tonight. Thank you to our speaker for the night. Have a great night, everyone. Good night.
Bye now.
What's this?